Okay, welcome back to Petrophysics Rocks. This is the final substantive chapter of the Petrophysics For Dummies series box set. This is one of my favorite subjects, but well, for the last 20 years anyway, I sort of really got involved in it in 2003. Before that, I kind of thought, well, you're not much of a petrophysicist if you need to rely on all this newfangled technology and stuff like that. But nevertheless, once you get into it, it's really, really interesting stuff. So this chapter is on NMR, which is nuclear magnetic resonance, which sounds very complicated. And if you've ever been in for an NMR scan on your knee or on your brain, well, I hope you're doing well now. But nevertheless, it really is the same sort of technology. Instead of a big machine around you, a big magnets around you sort of scanning your insides, these are tools that we put downhole and they magnetize on the outside, and the measurement is a lot noisier. When you talk to medical NMR guys, they can't believe what we're doing in the oil field with this stuff because the signal to noise ratio is so poor. But nevertheless, it's a fascinating subject. Now it sounds pretty daunting, but luckily there are some guys a lot smarter than me at MIT who are trying to sort of use technology or animation to show what a proton is. So we're reliant. This technology is involved in protons in the nucleus. Being magnetized and aligned, and you can see here this is a sign here on the left hand side is the scale. So as this bar moves across, we're getting smaller and smaller scales. So that's in the nucleus, if you like, and this one out here, that's the whole atom, if you like, with all the electron cloud around it and stuff like that. But as you zoom in, you get bigger and bigger magnification. You can see this illustration shows the protons in the middle, and you can see they're kind of wobbly, if you like. They're kind of asymmetric. They've got a couple of quarks in there and up and down quarks and things like that, but they kind of wobble about a bit, and you can see that they're not quite they don't spin smoothly. And so if you take a magnet and you can align them all together, then you can get them to resonate and sing out a big signal for you. Anyway, as I say, I left my proton magnetometer down in the garage, and again, my wife won't let me go out now and get it because I think it's about to rain. So I've had to make do with this more electronical stuff. You can check the link out at the top there. It's quite fascinating stuff. But hopefully this presentation will show you actually how we use it downhole to measure not just your kneecaps and your brain power, but the amount of oil in the reservoir, and it also gives you a flavor for how much of the oil can flow through the reservoir, more permeability indicators. Okay, if I've waffled on enough, sorry about that. Just I quite like this stuff, so I hope you can start to share some of my enthusiasm for it. Okay, so let's click on down here and get the NMR story. Let's see how we get on. Enjoy. There are a number of different pieces of information that we can get from nuclear magnetic resonance tools, and it's one of the more complicated measurements that we make. But underneath it all, there are some pretty simple and straightforward principles that I'd like to try and get across to you now. At the heart of hydrogen atoms, we have protons in the hydrogen nucleus, and these behave like little bar magnets. So they're all in all the water and the oil and the fluids downhole. And because they behave like little bar magnets, they have effectively a north and a south pole. If we run our nuclear magnetic resonance tool in the hole and activate a magnetic field, we can actually align all those protons in the fluids up together. And once they're all aligned, they start providing us with a signal by aligning them together and then applying some what's called radio frequencies out from the tool. We can wobble them a little bit, and we can measure the amount of signal we get back by moving these protons around together, and the way that they behave with each other can tell us a lot about the interaction that they're having, i.e. in the fluids, with the borehole wall, with the pore space walls, and that can tell us a lot about the underlying geology. It's probably simplest just if I show you. We make a measurement. Here's a raw NMR measurement. Now, not a lot of people potentially look at those types of displays, but what we're doing here is looking down on what's called the raw echo trains. So these NMR echo trains, this is what's called a VDL display, if you like. It's a display. Look, if we took a measurement at every depth in the wellbore, and we actually look down on it from above. So here we are looking down on these measurements. Now each one of these little speckly lines is a what's called an NMR echo train, basically. So here we have the raw echoes. There's no processing done on that. This is a raw measurement that the tool's making. Basically, we're aligning all the protons up together on the on the left-hand side of this display, and we get them, if you like, singing out a signal. We align them all up, and we get a nice big signal. And as we let that signal decay away through time, as the protons react with the pore space wall, they come out of alignment, and we lose this nice big coherent signal. So this NMR signal is proportional to porosity. So the higher the porosity, the larger the number of protons, because we've got more water or more oil in there, and then we align those all up, so we get a nice big signal. So we get a nice big red signal at early time here. So the higher the porosity, in this case you'll see I've put in some nice big pore spaces down here in this lower sandstone interval, and you can see that we've got a little bit better red signal than compared to this upper interval. So that is, if you like, the big porosity. That's everything all singing together, giving us a nice signal. Now, as we play some games with the tool, we let that signal decay away, and it gets less from left to right. And what I've done here is I've applied a heavy filter just to make it a little bit easier for you to see what's going on. So this is an extremely heavy filter, and it's just done for visual inspection purposes. If we look down again at the top of this heavily smoothed curve now, so instead of all these nice little speckly spikes, we're seeing just a lot of these green heavily filtered decay times, and so it makes it a little bit easier. You can see here we've got the nice big porosity, early time signal, everything's all aligned up together, singing out, giving us a nice signal. And then as we let that decay away from left to right, as we colour it in from red to blue, these protons are returning to their random ground state. And what you tend to find is that in large pores, where these protons are far away from the borehole wall, they don't tend to interact with the borehole wall, so they tend to stay aligned a lot longer. So they still can maintain their signal through time. So it stays red or green longer. In the small pores, where there's not potentially that much porosity in the first place, but what porosity there is, it rapidly decays away, because obviously the protons are very close to the borehole wall, and so therefore the moment that we let the signal decay, they return to their random non-aligned state very quickly, and the signal decays, and so we get a blue much earlier on in the signal. So here you see these flames, if you like, of high porosity and gradually decaying away. Now the bigger the porosity, the longer it takes for these flames to die away. But in the shales and the mud rocks, we very rapidly lose the signal as the protons return to their ground state. So one of the things we can do is we can look at that decay through time, and we can see how much signal are we losing in early time. If we're losing a lot, that means that there's a lot of this small pore spaces available, and so we invert the volume underneath these
these curves, if you like, and we can calculate the porosity at each time through the decay. So if we get a peak of porosity at early time, that means that we're losing large amounts of porosity quite quickly, so that's a quick decay. So we've got clay bound water, and if we've got porosity bins way out late in time, then that means we've got nice big pores that aren't interacting with the borehole wall, and we've got nice big pore space. So the volume of porosity associated with this pore size behavior, we can partition that into bins. And so let's run through that here. So we're calculating the amount of porosity at each stage in the decay, and the later the porosity, the bigger the bins, the bigger the porosity pore sizes it's coming from. So it's kind of like a pore size distribution. Now there are some complications with fluid effects and such like, but I don't want to complicate things too much with that. So generally you get a feeling for the amount of porosity and in what type of pore space it's in, and all of these bins sum up, if you like, if you take the total amount of space underneath the curve, that sums up to the total porosity seen by the tool, and that's actually independent of the matrix type, because we're just looking at the fluids here, which is kind of nice. So what we have here, if you like, is a T2 distribution. So if I took one of these curves, this is remember the integrated volume of porosity, and I just take one of those as an example out here. So the amount of porosity in this early time here is the clay-bound water. So this is the water held, it's very close to this pore surface, reacts very quickly. As soon as you take the magnets away, the alignment goes and you lose that quite rapidly. So that's the amount of porosity associated with the clay-bound fluid. Then there's a portion of the distribution that's associated with the capillary bound fluid. So this isn't actually held chemically within the rock, but it's held by wettability forces, capillary forces. This is the thin film of water that's held to the sand grains by capillary forces. Then you get out here into what's called the producible fluid, or the free fluid. That's this stuff here, right in the middle of the pore space. It takes a long time for that protons to return to their ground state. Nice big signal, big pore spaces. You can get fluids in and out of these things quite nicely, and we get oil and water. Both of those can be free. They both have similar hydrogen indexes, but that's the signal out here. So this is what we like to see. Nice big pore spaces, plenty of space for hydrocarbons and free fluids to hang around in and be produced through. So that's a nice understanding of the pore size. So here, when we take various ratios of this small pore size to big pore size, if you think back to that core plug, how easy will it be to blow from one side of the core plug to another? Well, if you've got a nice lot of big pores, obviously it's very easy, and if you've got a lot of small pores, it's very difficult. And there are various relationships out there that we can take this NMR data and we can plot up some ratios of the big pores to the small pores, and we can get an estimate of the permeability. What's interesting on this particular trace is that although the porosity, the NMR porosity, is quite similar, not too dissimilar, we see that the permeability down here in this lower sand is much better than the permeability in this upper sand. Even though the porosity, the amount of oil it can hold, is the same, this stuff here will be much higher permeability, and that's a function of these pore sizes, the pore size distribution. And that's a really key, a nice thing to get out of the NMR measurement. It doesn't just tell you the volumetric quality of the rock, i.e. how much oil you can store in it, which it can do. It also tells you something about the reservoir quality as well. So therefore it gives you a handle on this permeability. It isn't a direct measurement, but it can be calibrated on a field by field basis to give you a very good estimate of permeability. So in summary, There's a whole bunch of things that you can get out of NMR, porosity being one of them, these permeability estimates. You can also measure the amount of what's called irreducible water saturation, residual oil saturation. These are a whole bunch of petrophysical terms here that you may or may not need to know about, but there's a whole bunch of information in this NMR tool, and it's good for all of those things, particularly the last one, annoying accountants, because it tends to be, obviously, as you might expect, quite an expensive measurement. Although these days NMR is becoming more and more of a routine measurement to be made. There's clearly a lot of information in there, and doesn't just have to be for exotic applications. It can tell you a lot about your reservoir and how it's going to flow, and lots of other things that you might miss out on with conventional log analysis. So hopefully you could follow all of that. There's a rewind button. You can try it again if you can put yourself through it.